Good afternoon.
Good afternoon.
Yeah, only 8 participants going on right now. 8 of the best, right? All right. So we were on chapter 9. Let's see where we ended up here. Oh, first I want to talk about the exam. So as you saw, hopefully I graded the first exam. Okay, so I have your grades up there, and I've submitted the file that shows where I took points off. Hopefully today after class I will be able to have time to put the solutions up there. If not, I'll put them up tomorrow for sure. Okay, so that'll go up, and you can check to see where you did wrong. I'll probably go over the solutions on Monday. And then the other thing is, you saw I did a 10-point curve on the exam. This had to do with looking at the past averages of exam 1. I always look for a certain number of A's and then the class average based upon what should be expected for exam 1. It was the 10-point average. I don't necessarily know can't say whether you did, because there's a curve of 10, that it was that you guys did worse. I don't necessarily think that, because of the exam style is different, because I have those points coming off directly from your right or wrong answer, plus the work points that comes off separately. So those two could change my, the point structure of how I grade and take some points off with that method. So it might not be, it is a 10-point curve, but it might be just a little bit because the exam style has changed of why it's a 10-point curve. So if any questions with that, let me know. So we're on chapter 9. So I think we did the regeneration cycle, and this is where we have our typical Brayton cycle. We did the Otto cycle, so that's our closed system constant volume heat addition. We did the diesel, the closed system constant pressure heat addition. And then we did the Brayton cycle, which you see here, but it also has the regenerator here, where we're moving thermal energy from the, normally that would just be exhausted out, to preheat from 2 to 5 of what's going in the combustion chamber. So we have, right here is our heat out, right? And we have our combustion chamber has our heat in, and then our work out in the turbine, work in the compressor, and the difference between those gives us our work net. Okay, the regenerator, we see 1 to 2 is the compressor, 2 to 3 would be if we had just heat addition in our typical Brayton cycle. With the regenerator, we pull some thermal energy from one side, and that gets us to 5, okay, internally. So it's not any external heat transfer. And then 5 to 3 is where we have our Q in right here. Okay, and we expand to the turbine, and then out of that turbine we have our high temperature that we can move that thermal energy to the other side of what's going through the regenerator. Okay, so we get to 6, and then 6 to 1 is where we have our heat out. Okay, so we have Q in, Q out. 1 to 2 has our work in. 3 to 4 has our work out. Okay, so our work in and work out did not change at all, right? Because state 1 and state 2 are the same, state 3 and state 4 are the same. So the only thing that changes are Q in and our Q out portions. And then the equations, right? So if Q regen is that amount of heat that's coming internally is 2 to 5, that's what we have, the actual 2 to 5. The max would be 4 to 2. So the max would be our max temperature out of that turbine, which is at 5 prime. So between that 2 and 5 prime. Okay, so we have our actual over our max, right? That's our effectiveness, how good it is. So if it's 100% effective, that state 5 would be right at state 5 prime. So in this equation, basically the heat that we normally add from 2 to 3, so that Q in old or new or Brayton or whatever you want to call it, would be this one, this Q in would be equal to that one minus the Q regen actual. So this from no regen, this is our Q in that we have right here. And then this is our Q regen right there, okay, or there. All right, put in CP, we get this, and cancel CP. We can do our equations. We see here with regeneration at these low pressure ratios, we can increase the efficiency. At these higher pressure ratios, we actually decrease the efficiency because now we're trying to transfer heat from the after the compressor to the turbine in the wrong direction, right? As I showed the last class. So in these high pressures, it's exiting it here, and it's got this compressor exiting there, and we can't transfer heat now from here to here. Heat wants to go this way, okay? The wrong direction, versus in the low pressure ratio, we're good. We got heat. We got high temperature here, so we can transfer that heat this way and preheat here. All right, so now we said, and I heard you guys say it, right? Even through your microphones, you're like, give me more states, right? So we have 10 states. Here's our heat out. Okay, we have all these different states, and we work our way through, okay? So state 1 is our compressor, right? So we isentropically compress to state 2. Okay, and then we have our intercooler, so at constant pressure, we're rejecting heat, so there's some Q out there. So at constant pressure, we're rejecting heat, so we go from right to left, we decrease entropy. Okay, so that's Q out. And then 3 to 4, we isotropically compress again, so raise pressure and temperature, but we're keeping entropy constant. Okay, now we have our regen, where we get some thermal energy from the other side of the cycle, and it basically gets us up to 5, right? At constant pressure, we're adding this heat, we're adding this Q regen, and by adding that, we're increasing our entropy, okay? Go to our combustion chamber, we have heat in, okay? So we have our heat in, which at constant pressure again raises the entropy, so we go to 6, okay? Now we're at 6, we isotropically expand to 7 through the turbine, okay? We have a reheater that takes us from 7 to 8, okay, so we have some new heat in. And then we expand through the second turbine, isentropically to 9. And now we have a regenerator, where we're moving this thermal energy over, okay? From 9 to 10 gets moved 4 to 5. Okay, and then from 10, we're rejecting this heat to the atmosphere. So we have this Q out, okay? So when we look at this, we have work in here, work in here, we have work out, and work out here. So work net is all the work out minus the work in, right? So these two minus these two, or Q in minus Q out, right? For Q in, we have a heat input here and here, okay? And heat out, we have a rejection of heat here in the intercooler and a rejection of heat here when we go from 10 to 1. Getting from state 10 to 1. That's a heat rejection. Okay? So we got to basically just go through and work our way through the individual components, and we can march our way through this cycle. All right, the ideal jet propulsion cycle. Okay. It's used because it's light, compact, and high power to weight ratios. Okay. It's similar but differs from the Brayton cycle because its goal is different. Okay. The power produced by the turbine is equal to the power needed by the compressor. So that means the work out is equal to the work in. That means your thermal efficiency is zero, okay? Because that's not the desired output is not a work net out. Okay? It's something else. I'll get to that in a second. Okay, so the work net output is zero. Okay, so we have a jet propulsion cycle in the thermal labs that you'll probably get to run when you get to the second thermal fluids lab. Okay. All right. So the goal in these cycles, the desired output, is to accelerate that fluid out, so then the air or the gases to provide thrust to the aircraft. Okay. So using a nozzle here to accelerate the fluid. Okay. So it goes from a high pressure to a low pressure, and that decrease in pressure increases the kinetic energy. Okay, so there's two, you're accelerating the fluid in the opposite direction to give motion. Right? So there is two methods of doing it: slightly accelerating a large mass, which is a propeller-driven engine, or greatly accelerating a small amount of mass, which is a jet or turbojet engine, or both, where they combine some large amount of mass and small amount of mass to do it, and that's a turboprop engine. All right, so here is our thrust and our efficiency that we use for these. Okay, so we're wanting to get a propulsive force, which is the mass flow rate times velocity at the exit, mass flow rate times velocity at the inlet, mass flow rate equal. It's just the mass flow rate times the difference in the velocity. If we want propulsive power, we just now multiply that times the velocity of the aircraft. Okay, and that'll give us a propulsive power, which is our desired output. Okay, we're trying to get propulsive power, so that is our desired output. Okay, not the work net. All right, so what is this cycle, this TS diagram, and a typical, so here's a typical ideal turbojet cycle. We have 1 to 2, a diffuser. So we are decelerating the fluid coming in, and that raises the pressure and temperature up. Okay, from a drop in kinetic energy, you get an increase in pressure and temperature. Okay, so it's isentropic. And then we go through our compressor. So now we raise the pressure and temperature up. Okay, isentropically being shown. And then we have our combustor. Okay, so now we add heat, constant pressure, to raise the temperature up. So we have our heat coming in. Okay. Now we expand 4 to 5 to the turbine. Okay, so our turbine section, we're expanding. Okay. And then we have 5 to 6 is our nozzle, where we have our nozzle and we drop pressure and temperature again, but that goes to a increase in kinetic energy. Okay. In 4 to 5 in the turbine, that drop and increase in pressure and temperature is going to work, right? But in the nozzle, there's no work. It's going into kinetic energy. Okay. So now we have to 6, and then that gets exhausted out, where 1 is bringing in a fresh amount, a fresh temperature of air. So that means we have basically a heat rejection to bring us from state 6 back to 1. So that's our Q out. All right. So the other, as I mentioned earlier, this is the work out from the turbine. This is the work in from the compressor, 2 to 3 and 4 to 5, and those are equal. So there's just enough work by this turbine going into this compressor, right? There's no other attachment here for a shaft that's going to a generator. Okay, so the work out of the turbines equal to the work to the compressor. Okay. All right, kind of gives a breakdown of the energy. We have our heat in that we're putting in. We get our propulsive power. We get some excess heat that's got to be rejected off of what's coming in, and then we have some excess kinetic energy. All right, so then modifications. What's the kind of different layouts? I mentioned this already. We have the propeller driven. They're basically could be engines similar to just automobile engines, basically. But then there's prop jet, turbofan. So the turbofan, which you see down here, it has a large fan. So a lot of it goes around the surrounding of the engine. So we have this fan that then accelerates a lot of air around here. Okay. We also have the amount that's coming through here too. Okay, so they have this kind of combination there. So the turbine drives the compressor and this fan. All right, here you kind of see a layout of inside a turbofan in more detail with the thrust coming out. We have our compressor, high pressure, low pressure. We have our combustor, high pressure turbine, low pressure turbine. Okay, it's working its way through.
Quick question, Professor.
Yeah.
So by simultaneously adding heat or raising the heat and pressure, your change in entropy is lower or a constant?
So yeah, so here, if we raise pressure and temperature isentropically, yeah, then we increase. So this is a constant pressure right here. Here's another pressure. So we can increase from this pressure to that one isentropically. Yep.
I see now, okay.
Okay. So I was here. Okay, so we have a turboprop. So in this case, we have the turbine running a propeller. So the turbine's running the compressor and the propeller. So we have it accelerating using the propeller to accelerate a large amount of mass a little bit. Okay, but also we have the air coming through here, accelerating it a small amount, a lot. Okay. Here we show a ramjet. So this is missing the compressor and the turbine. Okay, so it's doing it, raising the pressure and temperature all with the diffuser right here, and then has the nozzle right here. So it's basically doing this all of our cycle here, where we have 1 to 2 through the nozzle, or through the diffuser, and 5 to 6 through the nozzle. It's basically doing the cycle this way. Okay, it's going 1 to 2, 5 to 6, or 2 to 5, 5 to 6, and around. So not having that section of it. This requires, movement. So a lot of times this one, they'll drop that plane off of another plane, because you have to have that velocity coming through here. There's nothing creating it, the movement of that air. All right, so second law analysis, gas power turbines. So what we see here is all just chapter 8. Okay, there's really nothing new. They've just combined things to make it easier to apply for a power cycle. Right here is all for a process. So we take, for a closed system right here, okay, here's the open systems. Okay, so here we have T-naught S-gen. We put it in our entropy balance, and then they substitute it in further For any individual process within that cycle of a closed system, we have this. If the process has heat in, we have this. If it doesn't, we cancel it. If it says heat out, we leave it. If it doesn't, we cancel it, right? So we can look at an individual process and get the X destroyed for all those processes. Steady flow system. Again, this one now has a open system, so we have the rate of entropy generation, and we put in our entropy balance for SGen. We get this, and again, we can cancel off terms depending upon the process and the device we're looking at, or the component. Here is if it's one inlet, one outlet, so they're just dividing out the mass rate. All right, so this is useful when you're looking at a single process to kind of get where is all the lost work? Is it in process 1 to 2, 2 to 3, 3 to 4? And now you can look at, okay, we're losing a lot of work here. Let's focus in on this. Or maybe there isn't that much, so maybe we can't. Okay? So it kind of gives you an analysis of where the lost work is. This section is about the whole cycle. Okay, whole cycle. So looking at a boundary around the whole cycle. Okay, if we put a boundary around the whole cycle, now the mass or the mass flow rate you have going on is inside your system. Okay, if it's a closed system, the mass is inside the system. So all you have crossing it is now the heat. Okay, so it simplifies to just the Q out and its temperature and the Q in and its temperature. Okay, same with for a open system, because again, your boundaries around the whole system, the mass rate going through the Brayton cycle, the gas turbine cycle, is all inside your boundary, so there's no mass flow rate crossing your boundary, so you just have the heat transfers, right? Because you don't have to worry about work when you're looking at the entry balance. So we just have T naught times that, okay? And then here's just close non-flow exergy and flow exergy. All right, so let's do some examples, unless there's a question.